Thank you. Thank you for this opportunity to speak with you. And I'm going to steal a pun from Prabhu. So it's going to get very dry in here. So yes, I'm Corey O'Hearn. I'm going to talk about local fluctuations in the shear modulus of granular beds. And so I'm going to motivate the problem through a fluid-driven granular bed. And then I'm going to sort of morph it into the fluid-driven, the flow is going to just be a perturbation to study the granular bed. So I'm very interested in the properties of the granular bed. And so I'm in mechanical engineering and material science at Yale, and I'm going to quickly tell you who does all the work. So my expertise is in computer simulations, and the students did those. So Dong Wang, Wei Jin are postdocs, and then I had a visiting student from University of Science and Technology in China, Shuyan Zhang. And then the motivation of the work is I have a long-term collaboration with Nick Willett, who is a professor at Yale and then moved to Stanford. And he carries out experiments of fluid-driven granular beds. And I'm going to show you some experiments or a movie from that work. And the student was Marios. The funding for the inspirational work is from the Army Research Office. And so over the past, say, 6 years, Nick Willett in his lab has conducted experiments of fluid-driven granular beds where he has a racetrack in an oval shape where the fluid can flow continuously. And then there's a test section where the granular bed exists and the fluid flows over that granular bed. And then there's a window where he mounts a camera and he can look down on the top of this granular bed as shown here. And as a function of the fluid velocity, he can look at whether the grains are moving on the surface and whether the grains have been entrained in the flow. And so we can look at movies like this and try to figure out which grains are moving and under what conditions. And a lot of this work has been published over the past couple of years. And so then where I come in is to do the sort of microscale, grain scale modeling and try to understand how erosion and the entrainment of the grains depends on grain scale properties like the static friction coefficient of the grains, the various boundary conditions, elasticity of the grains as well. And so the simulations sort of look like this, where here I'm sedimenting the grains and there's fluid flow in the background ongoing. The fluid velocity is below critical and I'm ramping it up. And as I'm ramping up the fluid velocity, you'll see in a second here that the grains will start flowing and be entrained.
Are there sidewalls here or no?
And so here the boundary conditions are periodic, sort of on the lateral walls. There is a fixed boundary on the bottom with no slip boundary condition, and then there's it's an open surface on the top. And so a lot of this work has been published, and so the way I want to approach it now is tell you about sort of the fascinating level aspects of the granular packings, and sort of use, it's sort of weird in this conference, but use the fluid driving as a way to study the properties of the granular bed. And the incredible thing is that even with all the complexities that I'm going to tell you in a minute, there's deep physics that we need to try to understand. And my argument is that we're going to start here and then build up from there. So the types of simulations and theoretical work that I'm going to talk about in this talk are in 2 dimensions, so not 3 dimensions, but from my point of view, that's not a big deal. So whenever I show you a 2D movie, just think of it as in 3D, but we can debate that if you want. There's going to be no static friction. There are no tangential forces on the grains, so the grain contacts just act normally. There's no gravity, but I'm gonna apply compression, and so I can have more pressure or compression on the packings. The particles are going to be spherical, but I'm going to talk to you about non-spherical particles at the end and how I can generalize my results to that. No fluid, because again, what I'm going to say is that on the one hand, I'm going to think of the fluid as perturbing the granular system, and so I'm going to just add perturbations, and they don't have to be fluid perturbations. And at first, I'm going to talk about quasi-static deformations. So there's no fast dynamics. And so the first idea that I want to get across is this, this jamming transition where the beds go from not being able to support stresses to a jammed configuration where they're rigid. And so the particular protocol that I'm going to show you now is a quasi-static compression protocol. But the particular protocol that I'm using is not that important. Just the fact that I get a jammed configuration is important. So just first, some details that aren't so important. Here, I'm studying two grain sizes. One is large and one is small. The ratio of 1.4 just to frustrate crystallization. In 2 dimensions, crystallization is very easy to generate. They're 50-50, so half large, half small. And what happens when I do this is that I'm going to go right to onset. And that means basically all the degrees of freedom in the system, which are the centers of the grains, are constrained by the contacts in the system. And I don't have more and I don't have less. I just have enough contacts, so all of the particles know exactly where they have to be. They can't move, or that's going to cost you energy. And so that number is 2n prime minus 1 for the particular boundary condition I'm in. I'm in periodic boundary conditions, so it's 2n minus 1. But basically, all you have to remember is that there are 2n, because there's the position of each particle. I have to determine where it is. The n prime is a little tricky in a little bit because some particles can be shielded from the system and not have any contacts. Those are rattlers or whatever you want to call. In this case, I'm not showing those. And so this is sort of what happens initially when you jam. But then what I'm interested in is what happens to the strength of the system as I compress it. And I want to study the strength of the system as a function of pressure.
Can I ask one other question, clarification? So you have these two families of particles, and you grow them until jamming occurs, right? Now jamming will occur first for a few of the particles. Others, in principle, could still keep growing. But I guess as soon as the first one cannot grow anymore, all the others of the same size also stop growing? Is that right? Okay, so I went a little fast. And so they're all growing uniformly. So I make a step, and they all grow uniformly. And then they'll you know, you could do different models, but the one I'm doing is I allow a little bit of overlap. And then what the computer does is it says, well, I want to minimize my energy, given that overlap. And so they'll move out. But they're only going to move out until there's no energy. So I haven't told you what the energy function is, but I'll tell you in a second. But basically, when they're overlapped, there's a repulsive energy. When they're not overlapping, there's no energy. And so then right when they all start to overlap is this jamming transition. So, sorry, I got a little ahead of myself. The simplest model you can do is this one, where the grains basically just have excluded volume interactions when the separation between the centers of the disks or the spheres is less than the sum of their radii. Then there's an interaction that causes them to repel each other. There's a force that causes them to repel each other. And then if the disks are not overlapped, there's no energy, there's no forces. A key parameter in this problem is the packing fraction, which is just the sum of the areas of the particles divided by the area of the box. And so there are no tangential forces. These forces just act normally, center-to-center forces.
So again, what we want to do is when you come upon a granular bed, it doesn't tell you, well, I'm not jamming onset. I'm at this, I have this number of contacts. And so we want to be able to study the properties of a granular bed as a function of various control parameters. The one I'm going to talk about today is the compression. And so what I want to do is the configuration that I just showed a second ago was just at onset. If you decompress a little bit, it's completely fluidized. You can move it around. If you compress it more, well, how does it change? And so at each value of the compression, I'm going to perform a simple mechanical test. I'm going to do a simple shear. And so this is an exaggeration, but what you can do is just perturb it infinitesimally and ask, what is the stress response to that applied, say, affine displacement of the particles? So what is its shear modulus? And that's relevant for fluid-driven granular beds because you're interested in what's the shear stress that will induce erosion or induce grain motion. And so I'm interested in the strength of these granular beds. And so the shear if you have this linear system, the shear stress will grow linearly with the simple shear strain, and then the shear modulus will be the coefficient in front of that increase. Just for technical completeness sake, I can calculate the stress tensor by looking at the virial expression, which is just in terms of the interparticle forces and the interparticle separations. The pressure is the average of the diagonal components of that stress tensor, and then I define the shear modulus. So what can the shear modulus, so what can the strength of these granular beds depend on? So the first thing it's not going to depend on is the particle modulus. I'm treating those as the same, all the particles have the same moduli, and I'm going to normalize all my measurements by that modulus. So it doesn't matter, in one sense, whether I'm studying steel or whether I'm studying plastic. I'm normalizing everything by that. I'm just interested in sort of the particle properties. So what can it depend on? First is that number of contacts. Does the system have 5 contacts? Does it have 4 contacts? How does that affect the strength of the material? What are the particular force networks? Are they aligned? Are they disordered? That will affect the modulus. And here's sort of the crazy uncle that's never mentioned, the frequency of particle rearrangements. How does that affect the shear modulus? Does anyone talk about it? And then obviously I have this control pressure, I have this control variable pressure. Is the modulus always higher if I'm under pressure versus lower pressures? So you may think this is crazy, but I think that we can solve this problem. Like we can basically calculate all the networks, where all the particles are, and we can develop a theory for the shear moduli of granular materials in terms of particles. And so that's why I think this is important. So what I'm going to talk to you right now is what happens to granular beds as they're perturbed. So the first thing that one thing that can happen is there can be a point change. That's just jargon, but I'll explain it to you. So what can happen is here you have a contact network for a jammed configuration that happens to have 2 rattlers, which means those positions of those particles are not well defined. I mean, there's enough space that they can be moved around and not sit on other particles. So the cavity where those sit is not small enough to confine them. Whereas every other particle, they can't be moved without costing energy. And so this force and contact network is stable and it's isostatic. Then what I'm going to do is I'm going to compress the system. When you compress the system, the particles are going to move. They're going to move a little bit. But then you can ask, is the contact network exactly the same? Like, are all the contacts exactly the same? The angles are going to change a little bit, but the contact network can stay the same. So that's what happens here. This intermediate configuration, if you look, all the contacts are the same. The angles moved a little bit. Then what happens And so you could ask, well, how did the shear modulus evolve when it went from here to here? That's a simpler question to answer. How did the shear modulus change given that all the contacts are the same? Then a harder question is, how did the shear modulus change when the contact network changes? And so here, this is a point change. The energy, the difference between the energy is continuous between this contact network and this contact network. But the shear modulus change is discontinuous. What happens here is you can see the particles are moving. I exaggerated, multiplied by like 100 or something to look at the displacements of the particles. So you can see these two particles are moving close to each other, or moving towards each other. And then when I make the small pressure change, these actually form a contact. And then all the other forces change a little bit to accommodate that new contact. So that's called a point change, where you can have a change in the contact network that's continuous in energy, but it actually causes a discontinuity in the shear modulus. And then you can have maybe one that you're more familiar with, where all hell breaks loose. These are avalanches. So what happens here is you start with some contact network, you compress it, and then you have lots of changes in the contact network over a very small change in strain. So here what you see is one of the particles becomes a rattler, this one, and then there are contacts here and here that form. And what you can do is look at the energy as you go from this state to this state, and you see that it's a discontinuity. That the energy was increasing as I compressed. The network was stable. It's just the angles are evolving a little bit, but no contacts are changing. Then the system becomes unstable. It has to rearrange to a new contact network, and now it's in the new contact network. And so you can ask, what does the shear modulus do? The shear modulus in the first contact network was looking like this. Then there's a rearrangement, an avalanche, and then the shear modulus continues.
Corey, the energy is the elastic strain energy.
The energy is, so when I was showing you the pairwise interaction of the particles, it was pairwise. It was just, is the particle overlapping or not? And so the energy there is just the sum of all the pairwise interactions between the grains. And so it's like a contact interaction. And so here is what you can look at, say, during the compression. Every compression step you look at, you can ask, what's the change in energy between those two compression steps? And what's the change in shear modulus? And they break into three groups. One is that nothing happened, that the contact network didn't change. And so what you can do is you can change the step size. If you change the step size between compression step and on a log scale, this will go to minus infinity. So those are continuous evolutions of the contact network. And then the two that I talked about, where the jump changes and the point changes, these are avalanches. And these are sort of avalanches as well, but maybe ones that people haven't thought about before. So the first thing was sort of rearrangements. The other thing that happens is, and I know it now, so maybe it's not so surprising, but the shear modulus, as a function of compression, actually goes down. And so I'll show it to you for a second, and I'll sort of drive it in a second, but that's a little bit kind of annoying, because you thought, well, if I compress the system, shouldn't the shear modulus go up? But this is the shear modulus when the contact network is fixed. And so I think about it a little bit like when I compress it or when I change the contact network, there's a possibility that there could be alignment of the particles, which makes the system sort of have a smaller shear modulus. But so here what I'm showing you is the shear modulus as a function of pressure, and they're all going down until there's a rearrangement. The way that you can look at this is you can write down an expression for the shear stress. You can say that the shear stress, or you can look at, say, the energy function. The energy function should depend on the shear strain and the volume. And when you do that, you can take derivatives of the energy to get the shear stress. And so there's one derivative of the energy with respect to shear strain. There's also a derivative of the volume with respect to shear strain. You get those two terms. And then the shear modulus is just one more derivative, is a derivative of the shear stress with respect to strain. You get three terms. One of them is always small near jamming onset, and you're left with two terms. One we found is basically a constant in the low pressure regime, and then the other term decreases with increasing pressure, and the coefficient is related to the strain dilatancy relation. And one sort of interesting aspect is for spherical particles, these sort of geometrical families for the shear modulus always go down, but if you look at different other particle shapes, they can potentially go up. So here's the crazy uncle. So this is the shear modulus versus pressure. And everybody likes to show ensemble averages. I fall into this trap as well. You know, you just show the average. Well, here I'm comparing the average to each configuration. So all the noisy data is each configuration on its own. The blue curve is the ensemble average data. And so the ensemble average data looks like maybe what you would expect. As the pressure increases, the contact number is increasing, the material is strengthening. But then if you look at any individual configuration, it's doing the complete opposite. If you look at an individual configuration, it goes down because of the effect I just talked about, and then there can be a rearrangement, and it'll rearrange to a new configuration. The sort of very interesting thing is that these shear moduli can go negative. So here's I'm doing something that I said I wouldn't do. It's the ensemble average curve. And so since some of the shear moduli can go negative, you know, I need to talk about that. So here's the ensemble average for just those configurations that have positive moduli. And then this is the absolute value of the shear moduli that can be negative. And so then the total shear modulus is just the difference between the two. And so how can a modulus be negative? So the way a modulus can be negative, so some people in the literature say, I don't want to deal with those, don't study those. Literally, that's what they say. But you can have a negative shear modulus. What you do is you just hold the boundaries. So that's what I'm doing. So if you have an experiment where I'm going to fix the strain, then you can stabilize a negative shear modulus, because what if you have a negative shear modulus and you're fixing the strain, the system's saying, I want to go, I want to move. But you're fixing the boundaries, so it's not going to move. And so the way to get negative shear moduli is to have an experiment where you're fixing the boundaries and not letting them move. So the interesting thing is, I'm going to show you a couple slides where magically everything collapses. The average values collapse if you plot things versus the pressure times n squared. It's amazing. So here I show you the fraction of negative shear moduli as a function of the pressure times n squared. So what you see is basically at sort of small pressures, there's a peak, but it occurs in the middle. So the negative shear moduli don't occur at the lowest pressures. They don't occur at the highest pressures. They occur when they're sort of just right at Pn squared equals 1. The other thing that's cool, and I would say this is part of the key, this is what I want to calculate theoretically. If I could calculate these distributions, this is the probability that you get a particular shear modulus. If I could calculate that theoretically, I'd be in really good business. I'm normalizing these shear moduli by the standard deviation. That's what this SG means. And what you see is there's some interesting evolution of the distributions with pressure. So they're really strongly peaked at low pressures, and then they evolve as you increase the pressure. And what's cool is that they collapse when you plot them. So you have to do a little fiddling, because you say plot them versus G star. So take out the average and then normalize by the standard deviation to sort of create a Z-score for the shear modulus. And they collapse at separate values of Pn squared. So if you have a low value of Pn squared, they look sort of like this skewed distribution. There's, very strongly peaked. But then when you increase Pn squared, you still get collapse, but you sort of have a family of curves at different Pn squared values. And so it sort of gets broader as you go to larger Pn squared values. And so that was sort of the first part of the talk, sort of looking at the distributions of the shear moduli. And now I want to sort of get more philosophical. So why do we ensemble average? We ensemble average because we think that the largest system that I could ever think about is a collection of smaller subsystems, and that those averages are the same. That's why I ensemble average. And so, does that work for the systems that I'm studying? So what I'm thinking about is I have a large system, and then I want to break it up into subsystems, and then ask, is the distribution of the shear moduli of the subsystems equal to the distribution that I get from the larger systems? And I want to ask that, you know, of course they're not going to be exactly the same because they have different numbers of particles in them, but I sort of, you know, trivially scale by sort of square root of n fluctuations. The difficult thing is, which I'll explicitly get to in a second, is how do you define the strain? You're defining the strain on a global scale because maybe you applied that. How do I define the strain on a local scale? And so some people, for example, in this paper, just say, well, it's going to be an affine strain. It's just going to be the same as the global strain. That's one way to do it. The other thing that I'm interested in is this sort of interesting plot. So what I want to do is I want to take a global system and then ask the global systems at a given pressure and a given system size, what distribution of local subsystems gives that same distribution? And what is the pressure and the system size that does it? This plot tells you that. It's a plot of the difference between those distributions, a score between 0 and 1. So if the distributions are the same between the global and the local, then delta P is very small. And so this is just a sanity check. Here I'm breaking up the system into sort of well, it's 2 by 2, so 4 boxes. And so those systems are still pretty big. And so I still get a small difference between the distributions when P prime n prime squared equals P n squared, where P prime and n prime were determined from the global system, and the P and the n were determined when I broke it up into local subsystems. Kind of an interesting fact is that this doesn't work the same when I break it up into smaller subsystems, but I can still do it. The slope on this log-log plot is a little bit different, so the P and the n have to change from the global system, but it still works. And so the exponent for that relationship is shown here as a function of the size of my subdomain. The other thing that I want to briefly mention is you can also, this has been shown in a recent paper, that if you look at, you can also look at spatial correlations of the local shear moduli. And if you look at spatial correlations in the really small systems, they show really long-range correlations. The angle correlation I'll get to in a second, but they show basically power law spatial correlations. And my question is that right? Should the local shear moduli be really strongly correlated? Should they be random? That's a question we want to get. So in the last minute or two, can this be right? No, there's no way it can be right. So here is the displacement field that I get when I shear a granular bed. So this is just some grain packing. I make a small, simple strain perturbation, and this is the displacement field. So it's not an affine displacement in every box. There's some non-trivial strain tensor that describes each local subsystem. So that's what we're dealing with now. So the first thing you have to think about is, well, I strained at some angle. Should I average over that angle? What should I do? So in general, what people have found is that when you strain at different angles, the shear modulus oscillates with 4 theta. That's just from the boundary condition. But there are 2 interesting parameters. There's the DC value, and then there's the amplitude of the sinusoid when you shear at different angles. And what's interesting is, in general, those 2 parameters are important. I've just been talking about 1. What people have found is maybe what you would expect. If you go to large pressures and large system sizes, there's an averaging that happens when you consider these large systems, and the amplitude of that oscillation goes away, so that you just have 1 parameter. So it doesn't matter which direction you shear, you always get a well-defined value. But at small values of Pn squared, they're comparable values, the amplitude and the DC value. So what I can get in the last minute is that here's what I want to do. So please invite me back to the next one. What I want to do is take this sort of non-affine idea more seriously, that look at, sort of decompose the system maybe into a Delaunay triangulation, so you can look at sort of each triangle where the vertices of the triangle are the particle positions, and then keep track of the stress and the strain on those triangles. And then you can sort of invert that, the stress tensor from the triangles and the strain tensor from the triangles to get a stiffness matrix. So what I've tried to say, so sort of conclusions, the shear modulus decreases with increasing pressure when the contact network is fixed. A key point in developing a theory for the shear modulus is that you need to sort of understand the frequency of the rearrangements, because they're going to cause these discontinuities in the shear modulus. When you do fixed strain boundary conditions, when you're fixing the location of the boundaries, you can stabilize configurations with negative shear moduli. And that can happen in experiments. We talked in detail about relating the distribution of shear moduli at different scales, and what assumptions go into that, and what you need to think about. That we want to calculate the local shear moduli without assuming an affine strain. And the other thing is that we're now moving in the direction of applying all these calculations to frictional and non-spherical particles, and I'd be happy to answer questions about that. Thank you.
Thank you very much for your great talk. So, we already have a question.
It's a very naive question. I mean, your entire presentation, you talked about shear modulus. What makes the shear modulus so special? Why not the bulk modulus or the elasticity modulus? Why the shear modulus?
Yeah, so that's sort of what I was getting at the end, is that the intuition first was that the shear modulus would differentiate, a non-rigid system from a rigid system. So that's the original idea behind the shear modulus, because anything can have, well, not anything, but lots of materials have a bulk modulus, but they don't have a shear modulus. So we're interested in this transition from being non-rigid to rigid. The important question is, how many numbers do I need to specify in order to characterize the macroscopic properties of the system? And that's an important question that no one knows. There are some thoughts on that is one number right at jamming onset, but the real question is, at finite pressure, how many elastic constants do I need to specify the system?
Corey, I'm hoping you can help me. We can go back a step, and I'm still trying to wrap my head around a negative shear modulus and what it means.
Yes.
Maybe it would help if you can explain how you calculate the stress and the strain, which presumably the shear modulus is the ratio of those two.
Yeah, so what I'm getting at is that, in simulations or in experiments, I have a choice of what to do at the boundary. And so I can do a constant force boundary condition or a constant stress boundary condition where I'm, controlling the force or the stress. I can do those. But you can also just say, I'm going to control the position of the boundary. And I'm going to apply whatever force. I said I'm going to fix the boundary. I'm going to apply whatever force is necessary to fix it there. If you do that, you'll generically get negative shear moduli, because the problem with negative shear moduli is it's unstable. It can run away, but I fixed it, so it by definition can't. So another way to describe it is that positive shear moduli, you're looking at sort of the energy landscape, or the energy plus sort of volume landscape, and those are positive curvature if you have a positive shear modulus. But I can explore states that have negative curvature because I'm holding the system there. Now, in nature, you can say, well, I believe in Newton, and so forces are important, or stresses are important, and maybe that's not going to happen. That's not going to happen because they're going to run away to the next state. But I'm saying definitely in experiments, there are experiments done where I'm fixing the location of the boundaries, and those states with negative shear moduli will occur.
Just a couple of questions so that I understand your simulations better. So you shear, I assume that your walls are rough, right? Because you don't have any frictional forces, you only have normal forces. So do you kind of glue some spheres to the walls so that they move with the walls, or how do you do that?
Yeah, so the first thing is that the main parameter I was varying was the compression. Mm-hmm. So I'm really interested in a property of the system as a function of compression. So the parameter I'm changing is, to some extent, the overlap between particles, the pressure. When I talked about shear, that I'm applying infinitesimally. So I described it as a physical experimental process. Yeah. But there are numerical ways to do it where it's truly infinitesimal. You take it all the way to 0, and it's just a property of the system that you have. But to answer your question, I could do it either way. I could have periodic boundary conditions, in which case the walls are rough because it's just like any other part of the system, so there's no slip. And an equivalent way would be I would have physical boundaries, they would be rough, and then I could also measure it that way. So I answered your question sort of 3 ways. The first way is you can literally take the derivative and take the infinitesimal limit. Mm-hmm. That's one way. Second way is, periodic boundary conditions is rough. And the third way is you could have physical walls that's rough.
Yes. Okay, thanks. And so if you have this, the walls moving like this and you want to compress, does that mean then the walls also move normal to their own plane at the same time? So that is that how you impose the compression?
Okay, so let me, again, so the main thing is I'm interested in the properties of a compressed system. Mm-hmm. So that's the thing I'm probing. The shear that I'm doing is just a measurement of a material property of that array of systems that I just studied.
So you compress at the very beginning.
Yeah, so let me just, great, thanks for letting me explain. So I showed you that movie where I'm creating a system that's sort of infinitesimally compressed. It just, you remember that movie? I grew the particles and then it created a solid that's sort of infinitesimally a solid. Just imagine keeping that movie playing. Just compress it a little bit more, minimize the energy, compress it a little bit more, minimize the energy, and I'm going to keep all of those configurations as a library of configurations, and then I want to tell you what the properties of those systems are.
All right, okay.
Hi. So presumably if you have bigger and bigger areas, then it would start to look more like affine on average, and there's a length scale associated with that.
I mean, if you're averaging, but I'm just saying it like so. Yeah. So do I believe in coarse graining? That's the. So if your system gets larger, then you're averaging over more stuff, and so it's definitely more isotropic. But I mean, I have to understand a little bit more about the question. If you go in and look, it's always going to be non-affine. So you'd have to ask.
Well, I guess as the system gets bigger, then that those differences become less significant over a bigger scale. Sure, if you look locally, there'll always be these non-affine variations, but they become less significant as the system gets bigger. They're smaller just compared to the size.
Well, so it's complicated because so what happens in that plot. I'll sort of blow your mind here, hopefully. So this is for a relatively small system, 64 particles. So now I study it for 64,000 particles. So what happens when you have 64,000 particles is the length of each of these segments becomes smaller. It's basically 1 over n, so 1 over 64,000. But the frequency with which they change becomes higher. there's non-affine behavior at the end of every one of these segments, and there's non-affine behavior at every separation between the segments. So there's more. So my point is that as you increase the system size, the frequency of the rearrangements gets higher and higher, and each of those rearrangements highly non-affine.
I mean, I guess the question is there a finite size associated with the rearrangements, or do the rearrangements span the whole system?
Yeah, don't know, but interesting question.
So, Corey, you only looked at frictionless particles, but suppose you did have friction, the minutest friction. How robust would this be, or how would it carry over to when you have frictional particles with the minutest friction? So specifically, would there be a single scalar shear modulus, or would it be a tensor?
So I'm just going to spout nonsense because I haven't done it yet, because I don't technically know the answer for frictionless particles. The thing which you know that happens with friction is that in these situations, there's a contact network, and then there's one force solution on that contact network. And so I specify all the contacts, and then I get just one force solution. In friction, I specify the contact network, and then I get a multiplicity of force solutions. So all I'm saying is that complicates the issue. My guess would be there would be an extra elastic constant, but I haven't done it yet. So.
Am I next? Okay, thanks. Well, that was fascinating, but you sort of did blow my mind a little here, so that maybe this question will come out strangely. But so, is there a relationship between? Okay, so presumably, since these are all plunging off and then rearranging, they must go to a higher value on average than they started with, right?
So,
do you have that relationship?
Yeah. So, at small pressures, it's a little more random, stochastic, that you can actually, because you can go from isostatic to isostatic. When you go from isostatic to isostatic, you're like, you see the scatter in the isostatic, the black lines at zero pressure. Mm-hmm. That's the scatter in the shear modulus you can have at zero pressure. So basically, it depends on where you are. Okay. Sometimes you can go down, sometimes you can go up. Mm-hmm. So if you go isostatic to isostatic, there's a little bit of stochasticity. As you go to higher pressures, you'll increase the contact number, and then that will dominate the answer. And so in general, you'll go to higher shear modulus.
Okay, so then the second part was when you said that you went to 64,000, these rearranged much more often. But does that mean that the distance that you proceed along this going down is much shorter?
Yeah. So the thing I definitely know is that the length of these segments is 1 over n. So they get shorter in pressure. So like the length of the pressure family goes as 1 over n. The rearrangements, I'm not as clear. It scales with n, but I don't know that exponent as well.
I was just wondering how the ensemble average, does it follow a very similar curve?
Yes.
Okay. So there must be a relationship between those. Thank you.
More question? Huh? Yeah.
Very quick one. So to make your life easier, let's go to the infinite friction limit, right? And you are isostatic. So that is well defined, right? I mean, infinite friction, isostatic. But the coordination number is going to be different. In that case, I think you will get an anisotropic shear modulus.
Yeah, I think I agree with that. I don't think people have proved that yet, but that's the direction I'm going. I think you can get anisotropic elasticity even with frictionless.
Okay.
Okay.
at finite pressure.
Well, thank you again.